This video is on redox titrations. So, like other titrations we did with acids and bases, it's used to determine the unknown concentration of a substance in solution. The equivalence point is when the reactants have reacted stoichiometrically by transferring electrons. So your number of moles of electrons transferred will equal your moles of electrons gained. Just like when we talked about before, just like moles of our solutes will be the same. Now we're talking about moles of electrons. These are going to be reactants between an oxidizing agent and a reducing agent. And the electrons are transferred from your reducing agent, which is what's being oxidized, because remember, oxidizing is losing. So this will lose electrons, and it will be transferred to your oxidizing agent, which is your substance that gets reduced, because reducing is gaining electrons. So these are commonly used in the food and beverage industry. Pharmaceutical industry. And water and environmental analysis. And you can read more about these specifics in your book. So the analysis of iron with permanganate. So in this, if you had 5 iron plus 2s, it will react with MnO4, your permanganate ion, which would be a purple solution. And you'd have 8 H pluses, which would then make your 5 iron plus 3s. So your iron is being oxidized, and the manganese, which turns colorless without the oxygen there, is what's being reduced. So you can note this reaction by a color change. So your your permanganate is your oxidizing agent, and the iron is your reducing agent. So electrons go from the iron to the manganese. All right, so in another one, what we have here is we have 2 I- ions plus an oxidizing agent will turn into iodine plus a reduced product. So oxidizing agents could be KMnO4, they could be KiO3, potassium iodate, they could be K2Cr2O7, potassium dichromate, or sodium hypochlorite, NaClO. All right, let's see. The I2 then is titrated with sodium thiosulfate using starch to signal the reaction. So then you get this 2S2O3 minus 2 ion plus the iodine, which is a really dark blue, which turns into your 2I minus and S4O6 minus 2. So something to note is that S2O3, because this will come up later, is what we call the thiosulfate ion. So this is a polyatomic ion that we just didn't use before when we talked about them. All right, the third kind of thing is the Winkler method. So this is used to figure out how much oxygen is dissolved in water, for example. This is an important indicator for the quality of water. As levels of pollution in water increase, dissolved oxygen content generally decreases, being used by bacteria instead. So the biological oxygen demand, or the BOD, is the amount of oxygen used to decompose the organic matter in a sample of water over a specified time, usually 5 days at a certain temperature. A high BOD indicates a lower level of dissolved oxygen. Usually, this means high pollution levels. A BOD of, let's see, BOD of less than 5 parts per million is not considered polluted. And we can use redox titrations to measure how much dissolved oxygen. So the Winkler method goes through a few reactions with your water sample. So first, your dissolved oxygen, you need to fix it. So what that means is we're going to take manganese. So it's 2 Mn plus 2. And you add that to your water. It'll react with the oxygen. And you're going to get 2 MnO2 plus 2 waters. And this will be noted by this MnO2, which is a brown precipitate. So in this reaction, the brown precipitate, the MnO2, then reacts with iodide ions and are oxidized. So you get your MnO2 plus it'll react with 2 I minus iodines and 4 H pluses to form Mn plus 2, plus I2 and 2 waters. So then that iodine produced, the I2, is titrated with sodium thiosulfate. So you've got 2S2O3 minus 2 plus the I2, which will form 2 I minus plus S4, O6 minus 2. So kind of the big takeaway from this is for every 1 mole of O2 in your water, 4 moles of S2O3 minus 2 are used. So if we can figure out how many moles of S2O3 are used, like if we can determine that based on concentration in our titration, we can do that conversion of a 4-to-1 ratio back to oxygen to determine how much oxygen. All right, so the way we get the 4-to-1 ratio is, I can write it out for you, for every 1 mole of O2. All right, and we can see that right here. All right, we can relate that to the MnO2 as a 1-to-2 ratio. I'll show you why I picked that one in a second. Okay, so your moles of oxygen cancel out because then our MnO2 is right here, which we can relate to our I minus. So for every 1 mole of MnO2, there's 2 moles of I minus. And then we can relate our I minus right here to our sodium just our thiosulfate. So for every 2 moles of this, there's 2 moles of S2O3 minus 2. So we've got 1 times 2 times 2 times 2 divided by 2, which gives us 4 moles S2O3 minus 2. So that's that 4-to-1 for oxygen. Okay, so here's where this applies. Let's say they collected 500 centimeters cubed of water, and they want to test it for oxygen. So they add that MnSO4 and they go through the whole process. All right, so then it was found that there was 12.5 centimeters cubed of this concentration, 0.5 moles per decimeter cubed of our thiosulfate ion. All right, so find the amount of dissolved oxygen in grams per decimeter cubed. So we need to know grams of oxygen in our volume of water. Okay, so how much? So to find our grams of oxygen, we can first relate it to this right here. Or I suppose this is a better way to put it. We can figure out how many moles of S2O3 there are because we have a volume and a concentration for our thiosulfate. So moles, which I'll do it in a different color. So moles, right, are your concentration times your volume. So this is going to be my 0.0500 moles per decimeter cubed times 0.01250 decimeters cubed. So my moles of my thiosulfate are 6.25 times 10 to the negative fourth. Okay, so now we can do that conversion to moles of oxygen. So it's my 6.25 times 10 to the negative fourth moles of S2O3 minus 2. And there's 4 moles of this in this reaction to every 1 mole of oxygen. And then I'm going to take this one step further because we want grams. So then I'm going to get rid of moles of O2 because I know there's 32 grams in a mole. Okay, so this gives me, if I type this all in, this gives me 0.00500 grams of oxygen. Okay, so now the question was, though, how many grams per decimeter cubed? So I've got 0.00500 grams of oxygen over 0.500 decimeters cubed, and that's right here. So it's 0.01, so 00 grams per decimeter cubed. That's our concentration of water in grams per decimeter cubed. So this is showing you kind of different ways to titrate and how we can relate that back to finding things like the amount of oxygen that is dissolved in water. And we'll do more examples with this, and I'll actually show you a video in class of what this titration, this Winkler method, actually looks like.